In today's lesson, we will talk about how to solve real-world problems that involve exponential growth and decay. In general, exponential growth works like this. Okay, it follows this model: y equals a times 1 plus r to the t power. In this model, the a represents the beginning amount, the initial amount. R is the rate, but written as a decimal. So for example, here it says that enrollment increased by 2%. So for this problem, R would equal 0.02, all right, because that's 2% as a decimal. You have to take the invisible decimal and move it twice to the left. So write an equation to represent the population P at RHS T years after 1998. Okay, so they tell us to use P, so I'm going to be obedient and do that. So P is equal to, all right, now we have the initial amount. Well, when we started keeping track here, the enrollment was 2,010 students. You know, they're in 1998. So then it would be 1 plus the rate, which is 0.02. All right, and we're just writing an equation, so I'm just going to put power of t. Now, rather than leaving this as 1 plus 0.02, I would rather that you go ahead and do this addition. 1 plus 0.02 is just 1.02. So 1.02 to the t power. So there is the equation or model. Now, what is the total enrollment in the year 2004? Well, from 1998 to 2004, that's a 6-year difference. Okay, so that is 6 years. So that will be our t value. So that means the enrollment will be, 2010, just using the formula that we just found, times 1.02 to the 6th power. And we can just put that in the calculator. All right, and I'm going to round this to the nearest whole student, all right, because you can't have half of a person. So 2,264 would be the approximate enrollment in 2004. Okay, what year will the enrollment reach 2,402? Let's use the table feature of our calculator to help us with this. All right, so if I hit the table button on the calculator, I'm just going to type in my model. All right, to the power of, and I'll just use x instead of a t. All right, I'm going to leave it at 0 for a second here. Okay, so looking at the table, at year 0, all right, that means the starting value is, of course, 2,010 students. Now, we're supposed to be seeing how long it takes. What year does the enrollment reach 2,402? So, as I go down, I see the enrollment's getting higher and higher every year that goes by. All right, so I'm looking for 2,402. So that is 9 years later. Okay. Now be careful. So I know that's going to happen after 9 years go by, but they're asking what year. So you can't just put 9, okay? You can't just say after 9 years. You have to say what year. In other words, 2000 what? So if we started off in 1998, then 9 years later, it would be just like doing 1998 plus 9. Okay, that would be the year 2007. All right, so that's a common mistake I've seen a lot of students, even though I'm asking what year, they will try to give me this t value, the number of years. So pay attention to what I'm asking you for. If I ask you for the year, give me a year, like 2007. All right, if the percent increase changed to 2.5%, then in what year will the enrollment reach 2,449? Okay, so 2.5%, all right, that means an R value of 0.025. So back in the calculator, go to the table feature. We just need to add in that extra decimal, all right, because it's 0.025 instead of just 0.02. So there it is. I think I'll just start at 0 again. All right, so here we are. So I'm supposed to be looking for 2,449. Okay, here's 2,448.9. So clearly this is about 2,449. So that's 8 years later. All right, so once again, that tells me that the t value is 8. But I asked for what year. Well, if 9 years later is 2007, then 8 years later will be 2006. All right, and that is how you do number 1. All right, let's take a look at number 2. Now, you buy $3,000 in gold coins as an investment. This increases at a rate of 4.5% each year. So write an equation. So they said use V, so I'm going to use V. First, the initial amount, which is 3,000. Okay. 4.5%, that means an R value of 0.045. So this is going to be 1.045, all right, to the t power. So this would be our equation. Now, if you made the investment in 1990, in what year will your investment reach $5,000? Okay, again, let's use the table feature of our calculator to help us. Okay, so $3,000, 1.045 to the x power. All right, we're looking for in what year will the investment reach $5,000? So let's scroll down until we get to $5,000. Okay. All right, it's somewhere very close to 12 years is the closest. Or 11 years might be closer. No, 12 years is closer. So we're talking about a t value of approximately 12. Now, what year is that? Well, we made the investment in 1990, so 12 years later, all right? I mean, think about it. 10 years later would be the year 2000. So 12 years later would be the year 2002. Okay, that's when the investment hit 5,000, 2002. All right, you sold the coins in 4 years. What would their value be? Okay, well, using the model, so 3,000 times 1.045 to the power of 4 for the 4 years. Since I already have it in the table, I can just scroll to 4. All right, so that's, I'll round this to the nearest dollar, so this will be $3,578. Okay, how much profit would you have made in 4 years? Well, if you started off with $3,000 and you ended up with $3,578, that's an increase of $578. All right, that's what's meant by profit. Okay, number 3. All right, this problem is slightly different. All right, buy a new car for a value of $24,000, but the value decreases by 16% each year. Now this is different because now we're talking about a value that decreases instead of something that increases. All right, this is called exponential decay. What we've worked with so far has been exponential growth. Now the difference as far as the formula goes is here's the formula for exponential decay. It's still going to be y equals the initial amount times, but instead of 1 plus the rate, it will be 1 minus the rate to the power of time. That's the only difference. Okay, so just be careful. Now this 16% translates into an R value of 0.16. All right, got to move that decimal twice. So this equation will become, they said use a value V, so I will. The initial amount is 24,000. So we will have to do 1 minus the rate, 1 minus 0.16 to the power of time. Now, rather than leaving this as 1 minus 0.16, I would prefer that you do the subtraction and wrote it this way. So 24,000 times. All right, so 1 minus 0.16 is 0.84. So I would much prefer that you wrote this as your equation instead of this. I will not mark this wrong though. So what will be the value of the car after 2 years? I'm going to go ahead and use the table feature this time because I can tell I'm going to have to use the table anyway, so I might as well. Show to the table, Batman. So 24,000 times 0.84, and I'll just put to the x power. All right, so sure enough, the initial value is 24,000. Now in 2 years, the value of the car will be $16,934. All right, and obviously I've rounded to the nearest dollar. How many years will you have owned the car when its value is 12,000? Okay, so the value is falling, so I'm just going to scroll down until, so 4 years, it's 11,948. I think that's as close as we're going to get. Yeah, 4 years, about 4 years. All right, if you bought the car in 2000, what year will it be when the car reaches a value of $5,000? All right, again, it says what year, not how many years. So you be sure you give me a year, like 2011 or whatever it is. So let's see, so $5,000. So we're going to keep going until it gets down. All right, 9 years later, it's pretty close to $5,000, like $3 off. So it's pretty darn close. So, but we got to be careful. So that's a t value. You know, we're talking about 9 years. But if you bought the car in 2000, 9 years later, you're talking about the year 2009. Okay, so make sure you put 2009 and not just 9 years. All right, that was it for number 3. All right, so number 4. Identify the initial amount, the growth factor. Okay, so the initial amount, maybe I can make little boxes out of this. The initial amount in trillions is 2.91. All right, so 2.91 trillion. Cubic feet of natural gas. All right, the growth factor, let's put a box around that. The growth factor is this number in the parentheses. So the growth factor is 1.07. All right, now the annual percent increase. Okay. Well, it comes from this 0.07, but they want it back as a percent. So that is 7%. Okay. So it's sort of like we're doing the problem backwards. All right. Use the model to estimate the natural gas consumption in 1955. Okay, well, first of all, we're talking about starting in 1940, because T is the number of years after 1940. So 1955, that's going to be a T value of 15 years. So that's the key, is that T is equal to 15. All right, from 1940. So now I'm just going to use a model. Okay, so 2.91, 1.07 to the power of 15. So that's 8.03. If I'm rounding to the same number of decimals we had, so 8.03. Trillion. Cubic feet. In fact, for cubic feet, I'll just put feet cubed, because that's cubic feet. All right, so we started off with 2.91 trillion cubic feet. In 1955, we were up to 8.03 trillion cubic feet. All right, that's number 4. Let's look at number 5. This looks like a typo. From 1970-01. That's not a year. So let's assume that this meant 19. Well, they say 1971. It doesn't really matter. All right. I'll just say, let's say it meant 1971. We're gonna have to use this 71 anyway, because that's how the T is defined. All right. Anyway, blah blah blah. The size of a microchip given by this formula. All right. So you can see that this value is less than 1. So you know that this is something that is decreasing exponentially over time. Okay, identify the initial amount. Okay, so the initial amount in this case is the initial size of the microchip in 1971. Okay, so that is 230 square millimeters. All right, and that's a short way of writing square millimeters, millimeter squared. All right, that's the initial amount, always right in the front. Okay, oh yeah, so that's the initial amount. I guess I should label these. Next, we got the decay factor. All right, just put an arrow. The decay factor is this thing in parentheses, so 0.7, whoops. 0.79, that's the decay factor. And then the annual percent decrease. Well, the percent decrease, we have to figure out what was subtracted to get us down to 0.79. All right, remember, so it's like 1 minus r is what this is. So that's equal to 0.79. So the easiest thing to do is just to understand that the r will just be 1 minus 0.79. And you can probably do that in your head. But otherwise use a calculator. So 0.21. All right, so that is the r value, is 0.21. Okay. So that means as a percent, which is what they asked us for, that's 21%. Okay, so just subtract from 1. That'll give you the decimal, and then just move that decimal back where it came from. Okay. Anyway, use the model to estimate the natural gas consumption in 1998. Well, from 1971 to 1988. Well, look, from 1970 to 1988 would be 18 years, right? Because 1970 to 1980, that'd be 10 years. And then 88, that'd be another 8 years. So that's 18. But since we're doing 1971, that's 1 year less. So that should be 17 years later. Okay, so we're talking about a t value of 17. All right, if you didn't like my little mental calculations, you could just do 1988 minus 1971. Okay, either way you're going to get 17. Okay, so with that in mind, then we're just doing 230 times 0.79 to the 17 power. All right, and this is the work that you need to show, is just writing this down. Okay. So the microchip's size at that point should be 4.2, let's say 4.2 square millimeters. Oh, wait, no, we're not talking about square millimeters. What in the world? Why does this say natural gas consumption? All right, that's a mistake. It shouldn't have said natural gas consumption. That was the previous problem. We're talking about microchips now. So use the model to estimate the average size. A lot of typos in it. I didn't write this, okay? Let me just say that as I see all these typos. You know I didn't write this. I don't use this font. I use Arial. Okay, this is not me. Use a model to estimate the average size of a microchip. In 1988. Yes, so like I said, 4.2 square millimeters, down from 230 square millimeters. That is a very tiny microchip. Deal with it. All right, let's move on. Okay, this explains why the cell phones were so big in 1970. They were giant, like, you know, like two bricks stuck together. That's how big the cell phones were. And now they are relatively tiny and light because they have a 4.2 millimeter microchip. Well, even that was 1988, so it's even smaller now. Anyway, number 6. I think this is the last problem in this assignment. In 1980, wind turbines in Europe generated about 5 gigawatt hours of energy. Over the next 15 years, the amount of energy produced increased by about 59% per year. So we're back to increasing again, so we're going to do the plus model. Okay, it says the amount E, so E, I use the letters that they tell me to. So in 1980, it was 5 gigawatt hours, so we start off with 5. And then 59%, all right, that is an R value of 0.59, all right, just move the decimal twice. So that makes this 1.59 is the growth factor, okay, to the power of time. So boom, there's your model, okay, I know you like it. Now, use your model to estimate how much wind energy was produced in 1984. Well, obviously, from 1980 to 1984, that is a T value of 4. All right, estimate the year when. So I can see in the part C, I'm going to have to use the table, so I'm going to go ahead and just use it now. Okay, so 5 times 1.59 to the power of time, I'll just have to use x. I like to start off at 0. Okay, so I'm starting off at 5. Now, they're asking for, 4 years later, how many gigawatt hours of energy? So we're already up to 31.95. So I'm going to go ahead and round that to 32. Okay, so it's about 32 gigawatt hours of energy. Okay, great. Now, estimate the year when 80 gigawatt hours of energy are produced. Again, they want the year, not just a number, not just a T value. So let's look for that 80. All right, so we're at 31 so far. Whoa, that was fast. All right, 80, boom, it's very close to 6 years later. Okay, so I like to write down that T equals 6. All right, but that's not what they asked us for. So starting in 1980, 6 years later, of course, would be 1986. Okay, so kabam. That is how you do number 6.